Hello students, welcome to my lecture which is based on applications of Gauss theorem. Gauss theorem is used to find the electric field intensity due to symmetric charge distribution. And in order to find the electric field intensity at a point outside a charged sphere or electric intensity at a point outside a charged cylinder or electric intensity at a point near and outside a charged conductor of any shape or electric intensity at a point due to long thin sheet. We must follow the following 5 steps. So in each application we have to follow 5 steps, and the first step is describe charge distribution. That means describe charge distribution in terms of linear charge density, in terms of surface charge density, or in terms of volume charge density. This is the first step. Second step is that construct Gaussian surface which encloses charge. So Gaussian surface is nothing but a purely imaginary surface which encloses the charge. So this is the Gaussian surface in the form of sphere and which encloses the charge which are deposited on the inner sphere. So this is Gaussian surface which is imaginary surface which encloses the charge. And on this Gaussian surface the electric intensity at all the points is same. Electric intensity at all the point is same, and the electric flux is directed normally outwards. And if we construct the Gaussian surface, then find total normal electric induction over this Gaussian surface. And the equation so obtained, say that equation number x. The third step we have to follow is find out the value of total normal electric induction using Gauss law and say that equation which is to be suppose y. And the fourth step is that equate right hand sides of equation x and y. And finally we get expression for electric intensity. So to study the applications of Gauss theorem, we have to follow these steps. If these steps are followed, then it is very easy to understand the applications of Gauss theorem. Now, first application of Gauss theorem is electric field intensity at a point outside a charged sphere. So this is the first application. In order to study this application, the sphere is a hollow sphere or it is a spherical shell. Now consider a sphere A having radius equal to small r, and on this sphere charges are deposited uniformly, and this sphere is kept in a permittivity of medium epsilon is equal to epsilon 0 k, and the distribution of charge is a surface charge distribution, and therefore sigma is the surface charge density, and which is equal to q divided by area of sphere A. Now construct an imaginary concentric sphere known as Gaussian sphere whose radius is equal to small r, and in this case this is the sphere B, and radius of sphere B, that means small r, is greater than the radius of sphere A. So this is the Gaussian surface, and this Gaussian surface encloses a charge distributed on sphere A. Again consider a point P on this Gaussian surface and take a small area ds around this point P, and therefore the electric intensity at point P is directed normally outwards, and we have to find the electric intensity outside a charged sphere A at a point P, and this point P at a distance of small r from center of sphere A. Then total normal electric induction over a entire sphere B is given by integration epsilon e cos theta into ds. Suppose this is equation number 1. But in this case, as the area ds and electric field intensity are perpendicular to each other, the value of this angle theta is 0, and therefore cos theta is equal to 1, and our equation number 1 becomes TNEI over sphere B, which is equal to integration epsilon E into ds. equation number 2. Equation number 2 can also be written as TNEI over sphere B, which is equal to epsilon E integration of ds, and the integration of ds is equal to the surface area of sphere B, and it is equal to 4 pi r square. So substituting the value of surface area of sphere B in above equation, again we get TNEI over surface B or sphere B, which is equal to epsilon E into 4 pi r square. So this is our equation number 3. So first step is followed, distribution of charge, which is surface charge density. Then second step is followed, Gaussian surface is constructed and total normal electric induction over the Gaussian surface is calculated, and which is equal to epsilon E into 4 pi r square. Then by using the Gauss law, total normal electric induction over closed surface, that means closed surface, that is sphere B, is equal to total charge enclosed by the sphere B, and the total charge enclosed by the sphere B is equal to Q, and say this equation as 4. Then equation 3 is equal to equation 4, and we get epsilon E 4 pi r square is equal to Q, and therefore expression for electric intensity at a point outside the charged sphere is Q divided by 4 pi epsilon r square. So 1 upon 4 pi epsilon 0 k, or E is equal to 1 upon 4 pi epsilon 0 k into Q divided by r square. So by using Gauss theorem, we have find the electric field intensity at a point outside a charged sphere, and which comes out to be E is equal to 1 upon 4 pi epsilon 0 k into Q divided by r square, which is same as we have calculated by using the Coulomb's law in standard element. So Coulomb's law and this Gauss law are analogous to each other. Now the expression we have derived is in terms of charge. Then this expression for electric field intensity in terms of a surface charge density can be obtained, as we know that surface charge density of sphere A is equal to Q divided by A, that means area of a sphere A, which is equal to Q divided by 4 pi capital R square. And from this equation, the charge on sphere A is equal to sigma into 4 pi r square. So this is the value of charge deposited on sphere A in terms of surface charge density. If the value of this charge Q is substituted in the expression for electric intensity, then E is equal to the value of Q. Value of Q is sigma into 4 pi capital R square divided by 4 pi into epsilon into small r square. As this 4 pi gets cancels, then we get the final expression for electric field intensity. E is equal to sigma into capital R square divided by epsilon r square. So this is the expression for electric intensity in terms of surface charge density. Electric field intensity at a point outside a charged sphere is given by formula E is equal to sigma into capital R square divided by epsilon into small r square, where capital R is the radius of sphere on which charges are deposited and small r is the radius of Gaussian sphere which encloses a charge. Now, if point P is on surface of sphere A, then in that case the small r is equal to capital R, and therefore the electric field intensity at a point on the surface of conducting sphere is given by formula E is equal to sigma divided by epsilon, or which is equal to sigma divided by epsilon 0 k. And if point P is inside the sphere A, then electric field intensity E is equal to 0. So electric field intensity inside a charged sphere becomes 0 because surface does not encloses any charge. Now we will discuss second application, electric field intensity at a point outside a charged cylinder. And in this case, this cylinder is thin and infinitely long. Now suppose that a cylinder A having radius equal to capital R, on which charges are uniformly distributed, and this cylinder is kept in a medium of permittivity epsilon is equal to epsilon 0 k, and again consider that lambda is the linear charge density of the cylinder A. Then to find the electric intensity at a point from the axis of this charged cylinder at a distance small r, construct an imaginary cylinder known as Gaussian cylinder with radius is equal to small r, which is coaxial with the cylinder A. So this is a Gaussian cylinder, and this Gaussian cylinder encloses the charges. Now take a point P on the curved surface of this Gaussian cylinder and again take a small area ds around the point P. Then electric intensity at every point on this curved surface is directed radially outwards. For the flat surfaces, the electric intensity is zero because no tubes of induction are passing normally through the flat surfaces or flat face of the cylinder. Then TNEI over cylinder B is given by integration epsilon E cos theta into ds. But here area ds and electric intensity are perpendicular to each other, therefore cos theta is equal to 1 and therefore this expression becomes TNEI over cylinder B is equal to epsilon E integration ds, where integration ds is equal to 2 pi r into small l is the surface area of cylinder B, and hence TNEI over cylinder B is equal to epsilon E into 2 pi RL. So this is expression number 1. Again, from the statement of Gauss theorem, the TNEI over cylinder B is equal to algebraic sum of electric charges enclosed by the cylinder B, and which is equal to Q, which is equal to lambda into small l. So this is equation number 2. Then equating 1 and 2, we get epsilon E 2 pi r into L is equal to lambda into L, and hence we get the value of electric field intensity at a point outside a charged cylinder, which is equal to 1 upon 2 pi epsilon into lambda divided by small r. So this is the expression for electric field intensity at a point outside a charged cylinder in terms of linear charge density. And if we multiply and divide by 2 to expression for electric intensity, then we will get electric field intensity is equal to 1 upon 4 pi epsilon into 2 lambda divided by small r. Again, this electric intensity can also be written as E is equal to 1 upon 4 pi epsilon into 2q divided by r, where this q is equal to capital Q divided by L, charge per unit length. Again, the expression for electric field intensity outside a charged cylinder can be expressed in terms of sigma. As we know that surface charge density of cylinder A, which is equal to capital Q divided by area of cylinder A, and which is equal to Q into small l divided by 2 pi small r into L. So L gets cancels. Therefore, charge on cylinder A, Q is equal to 2 pi r into, here this is capital R is the radius of cylinder A. So 2 pi capital R into sigma. If the value of this Q is substituted in the expression for electric intensity, which is E is equal to 1 upon 2 pi epsilon into Q divided by small r, which is equal to 1 upon 2 pi epsilon into value of Q is 2 pi capital R into sigma divided by this small r, then 2 pi gets cancels, and therefore the electric field intensity at a point outside a charged cylinder in terms of surface charge density is given by formula sigma into capital R divided by epsilon into small r. Again, if the point P is on the surface of cylinder A, then small r is equal to capital R, and hence electric field intensity on the surface of charged cylinder, which is equal to sigma divided by epsilon, or which is equal to sigma divided by epsilon 0 k. If the point P is situated inside the charged cylinder A, then electric field intensity is 0. If the charges situated on the cylinder A or the charged cylinder is positive, then electric intensity is directed outwards. If charges are situated on the cylinder are negative, then electric field intensity is directed inwards.